Welcome back again. Just to start off, I will remind you that problem set 1 was just due. If you haven't done it, or people out there in TV land who haven't done it, you can still turn it in for a week, but it's half credit. And I did put up the second problem set, which will be due next Wednesday. And because it's due only next Wednesday, it's going to cover material that I'll talk about today in the context of seesaws and a little bit in the world of wheels, most importantly, friction, which comes up right at the start of wheels. And why do you have wheels? It's to deal effectively with friction issues. All right. Any class structure-y things to chat about? All right, well, a couple of questions that came in last time and I didn't get a chance to deal with. Talking about ramps, I've got one that's in our future in the next, down the road too, but talking about ramps, so a wagon on a ramp, just to make sure everybody's on board with the issues here. If you have something that moves essentially freely, like a wagon with wheels, okay, it gets rid of friction. If you have a wagon on a ramp or a ball on a ramp, it experiences two basic forces. Let's set aside the ramp force for a second. It experiences its weight down because it's here near the surface of the earth, and it experiences a support force up at an angle because the ramp isn't horizontal. Support forces are always at right angles to surfaces, perpendicular surfaces. So the support force I get from the wall by pushing on it is going to be horizontal toward me because the wall over there is vertical. This is the perpendicular. So the two forces on a ramp, on a wagon on a ramp, are weight down, support force up and to the side, and those two forces together, when you add them to find the net force on the wagon, they don't cancel, they add to a little leftover. That little leftover is, I call it the ramp force. It happens to point right down the ramp. And the strength of that summed ramp force depends on the steepness of the ramp. The steeper the ramp, the stronger that force gets. So hopefully this is review for you. If not, ask me again about it. If that's the only force that the wagon experiences, if those are the only two forces that the wagon on the ramp experiences, the wagon then has a net force that is the ramp force, and it accelerates downhill. And that accelerating downhill, it's the wagon experiences it. If you go skiing, downhill skiing, you experience it. If you ride your bicycle down a hill, you experience it. It's all over the place. Familiar. It's what gets you picking up speed, going downhill. Now, typically with a grocery cart or something like that, where you kind of want to keep it under control, you don't actually let go of the grocery cart on the hill and let it roll down. It's something bad's probably going to happen. So instead, you do things like you exert your own additional force. This would be the third basic force on the cart, pushing uphill. And if you push uphill just enough to cancel the ramp force, then the three basic forces acting on the cart, weight down, support force up at an angle, and your force up at a different angle, the three of them conspire to sum to zero. And the wagon then is experiencing zero net force. And if you remember, zero net force means no acceleration. We can say that the grocery cart, the wagon, is inertial or coasting, either one. They mean the same thing. And I asked you a question last time, which you never really, we never got unanimity towards the right answer. But the question was like, okay, so if it's in this situation of experiencing zero net force, that wagon, what's it doing? Well, you don't know what its velocity is. All you know its velocity is constant because it's inertial. All those forces sum to zero. So it could be motionless on the ramp, or it could be going up, or it could be going down at constant velocity. Is that okay? One of the questions asked is there always a force with the equal in magnitude of the ramp force? That is presumably a force uphill. No, something's got to be exerting it. So if you're not there, that wagon's going to roll downhill. Or when you park your car on a hill, you put on the brakes, which, as we'll see sort of down the road, that asks the ground, by way of a force that we haven't encountered yet formally, friction, to push uphill just enough to keep the car from accelerating downhill. So if you leave out those forces that cancel the ramp force, things are going to go accelerating downhill. All right? And I will remind you, I said it last time, and whether I said it clearly enough or not, to actually take a wagon up a hill, it's all very well to travel at constant velocity, but at the start and the finish, you're not going to be at constant velocity. For example, you typically want to get the thing started from rest. So the wagon starts down on the low level at rest, and you want to get it moving up at constant velocity. So at least briefly, you're going to have to exert interesting, complicated forces on it to get it to accelerate such that it's heading up the ramp. You have to push extra hard, harder than anything else in the story. And so once that's done, and once the wagon is going uphill at the speed you like, now you can back off and simply cancel the ramp force. That's all you need to do. The wagon will then coast. And the fact that it's coasting doesn't mean you're not doing work on it. You are doing work on it. Just to bring you back to remember work and energy was important in this story. You are doing work on it, pushing the wagon up the hill, because you're exerting a force on the wagon, part one, for doing work, and the wagon is moving a distance in the direction of your force. Ergo, you're doing work on it. So you take it up the hill, up it goes, and at the end, of course, you want to stop it again. You don't want to keep pushing it up the hill forever, so you change the force you exert on it such that it slows to a stop. For example, you don't push uphill enough. It slows down, comes to a stop, you're done. All right, any other questions about ramps? I think I can leave them in our past. Thank you, I won't read this one. All right, my haircut. Yeah, it's fun. All right, so I'm going to move on to seesaws, the world of seesaws. And why seesaws? And I'll tell you, just to look in the back, I've tried different topics for this story. This is a story of rotation, rotational motion. I've tried things like windmills and stuff, and okay, I'm back at seesaws. The sad thing about seesaws is they're rare these days. They were everywhere when I was a kid, back, when the dinosaurs were roaming around. I think they, like several children's toys, sort of got scarce because they're a little dangerous. Those of you who have played on seesaws know that if you have two friends that really, you work together well and you're old enough to realize that there are consequences to what you do, they're fine. But when two of you are playing seesaw and one of you you're in the air like this and the other kid decides they're bored and they jump off, thunk, you drop like a rock, swallow your gum, bite your tongue, whatever. So they're rare, but there's still a few of them in Charlottesville. Anyhow, why seesaws? And why do this at all? It's the story of rotational motion. And much of what we'll do over the rest of the semester won't be rotation. Won't involve rotation, but some of it will. And so it's worth just setting the stage for some of that stuff. And furthermore, you live in a world where rotation happens a lot, and might as well have some tools for understanding it. So the seesaw, it rocks back and forth about a pivot, and it doesn't go anywhere. It sits there, but it rotates. And it's that motion that we're going to look at, or that we do look at, and I'm going to try to illustrate for you. And just to flesh the whole thing out quickly, you look under the hood, the physics issues that live in this world of rotation, they are very similar to the world I've been describing for you up until this point, the world of translational motion. So just to make sure this is clear, to pass this along, two types of motion. Translational motion means going somewhere. So this is translational motion right now. I'm clearly moving. My position is changing, for example. And describing my motion, you describe it in terms of my position, or you can look at my velocity or my acceleration. And these accelerations are caused by forces, and my resistance to acceleration is my mass. Those are the physical quantities of translational motion, going somewhere. And we came across three sort of important laws, the so-called Newton's laws. The fact that they're given names and such and whatever means that other physicists talk about them, at least in introductory classes. We'll see down the road that Newton's first law is a consequence of sort of other laws. It's, are they super duper duper fundamental? Maybe. But I've given you the Newton's laws for translational motion. And I'll remind you what they are. And I'm about to give you Newton's laws for rotational motion. Remember, the first one was that an object that's free of external forces, or has no net force acting on it, coasts. It moves at constant velocity. Remember that one? The idea of, it's the codification of this notion of inertia. The second one, which actually is one of the rare laws that I hope you actually remember. As it's a formula, and I hope you remember it. And that law was how forces cause acceleration and mass resists it. Remember that? It's the idea that if you take the net force on an object and divide it by the object's mass, that is the acceleration of the object. It's, you may remember it as F equals ma, okay, but my version is meant to be conceptually more practical. The force on the object, that is the net force, divided by its mass, that tells you how it accelerates. All right? That equation's worth remembering. The one other one that's worth remembering this semester, I think, is the work one, the work equation. When you do work on something, you exert a force on it, and it moves distance, direction of force. It's the product of those two. The work you do, the force you exert times the distance the thing travels, the direction of the force, that is the work you do. Quantitatively accurate. All right? So Newton's first law, I did that. Newton's second law, I did that. Newton's third law, that was the idea that if you push on something, it pushes back equally hard in the opposite direction. And we're done. Okay? Any questions about the 5 physical quantities of translational motion and those 3 laws of motion? Anybody want anything? Can I repeat the definition of translational motion with respect to Newton's laws? So in translational motion, it addresses things like velocity. So Newton's first law looks at velocity and says, well, if there's no net force on something, its velocity is going to be constant. It's going to translate steadily. Newton's second law says what causes changes in velocity. Well, velocity is a translational quantity. What causes changes in velocity, namely accelerations? And those are forces. So forces are the influence of translational motion. They affect and change translational motion. And because forces are translational motion quantities, they clearly show up in Newton's third law for translational motion. Okay? Now, let's shift over to rotational motion. And I'll tell you, rotational motion is, you can describe anything that's rotating in terms of the translational motion of all its individual little parts. And therefore, as a result, rotational motion is not fundamentally completely different from translational motion. You can describe me rotating in terms of which way my fingers are moving, which way my nose is moving, all the accelerations and all the forces, but it's messy as can be. So you do better to just like go, oh, there's actually a simpler way to look at how this kind of motion works. And it's rotational motion. All right? So in rotational motion, we have, again, 5 physical quantities. And we have 3 Newton's laws. And they're analogous. So if you get one, you can work to get the other. The rotational ones are a little messed up. They're a little more complicated. We'll see that. And I'll do it. So in rotational motion, there's something that's like a position and something like a velocity and something like an acceleration. What are they? They're associated with orientation. So instead of having a position like where I am translationally relative to some reference point, which, remember, position is a vector quantity, there's angular position, which is how I'm how I'm turned, rotated, relative to some reference orientation. Like facing you could be the reference. That could be 0. And this is you could say it's a 90-degree rotation. You okay with it being 90 degrees? And I'm now going to address another question that came in about right-hand rules. So this is a 90-degree rotation. So my orientation, my angular position has changed from 0 to 90 degrees, but that's not quite enough information because 90 degrees is this, but so is this. This is 90 degrees, and this is 90 degrees, okay? So there are a variety pack of 90 degrees. Just as with position, remember position? This is the reference right here. I'm 6 feet. I'm 6 feet away, but I'm also 6 feet away, or I'm also 6 feet away. You need a direction with position to pin down where I am. I'm 6 feet away, but in which direction? So with the rotational quantities of motion, you also need a direction to them. Oh, that's tough. What's the direction of, this is 0, this is 90 degrees, what's the direction? So the convention for the direction, oddly enough, there are more than one choice, but there's a semi-obvious choice for how to define the direction of this 90-degree rotation, and therefore my new angular position. And the semi-obvious choice is this. Run a rotisserie skewer through me and rotate me about it. It's a vertical skewer, and I've been rotated, right? 90 degrees. And this is 90 degrees about that vertical skewer. So the direction I rotated is defined as a vertical direction. I rotated 90 degrees in the vertical direction. You know, you might think, well, what's vertical got to do with it? There's nothing that went up or down. It's okay. It's just you've got to pin down how to describe this. You could use other terminology, for example, go above me and look down on me. This was a counterclockwise rotation, 90 degrees. That would do it too, but it's wordy as can be. It's better to say this is a 90-degree vertical rotation. You okay? There's one problem with that, and that is this is a 90-degree vertical rotation. This is a 90-degree horizontal toward you, or along this way rotation. So those are distinguishable for sure. But this is 90-degree vertical, and this is 90-degree vertical. Uh-oh, there are two choices. You can take that rotisserie, and you can spin it one way, 90 degrees, the other way, 90 degrees. They're both vertical. So what do people do? They thought about this for a while, and they finally decided, the vertical direction has vertical has two directions along it, up and down. You got two choices. Let's name one of them up and one of them down. So this could be up, this could be down, or vice versa. You okay? Now you can make it unambiguous, but you have to agree on which one's up. So what's the rule that came out? And this is the right-hand rule. Somewhere down the road, they came up with a rule based on right hands. It turns out that just by sheer telephone, you all grow up knowing which is your right hand. But you can't tell a space alien, if you try to tell a space alien which is their right hand, assuming they've got two hands, which is their right hand by telephone, you can't do it. They actually need an artifact, or they have to have seen a right hand to know. Because otherwise, nothing you say, this is one of these peculiar things about nature, is nothing you say can distinguish right from left. It has to be based on an artifact, on people looking at it and agreeing, that's right, that's the right hand. If that makes no sense to you, go think about it late at night and you'll realize, oh my, you can't do it. Okay? So we carry with us an artifact, most of us, from childhood, which we know is our right hand. And the deal is this, the right-hand rule says, if you curl your fingers in the direction of the rotation, or something associated with the rotation, my right hand, and I don't care if you're left-handed, sorry, you've got to use your right hand. If you try to use your left hand, it'll be all backwards. You'll be living by the left-hand rule, and no one will talk to you. So, so you come around with your fingers are go swoop that direction. Which way is your thumb pointing? Up. So this is by convention, the right-hand rule convention, up. 90 degrees up, okay? And this, 90 degrees down. They're different. You okay with that convention? Will you remember it? Who knows? But I'll tell you something. Again, tools for a living. Nearly everything around you that involves screw threads, like screws, like jar lids. Yeah, I've now finished the list, but there may be the other things that are threaded things that you spin them to make things happen. Faucets, but faucets are messy. Faucet handles. Screw threads for sure, and jars for sure. They follow a right-hand rule. If you want to open a jar, how do you open the jar? The threads are such that they're right-handed. You take your right hand, you sweep your fingers in the direction of which way you're going to turn the lid will move in the direction of your thumb. You want to open the lid? The jar's sitting here, here's the lid. Which way do you turn it? This way to get the lid up. You want to put the lid on? This way to put it down. You okay with that? Screw threads, you're putting in screws, over here you're trying to screw a screw into the wall. You want it to go into the wall, rotate it this way, inward. Your fingers turn this way, you're righty-tighty. Your thumb points the direction that the screw will move as you turn it that way, but with your right hand always. There do exist left-handed threaded things. When you run across one by surprise, it's a shock. I mean, I've discovered them once in a while. You're tightening, it's getting loose, or worse, you're trying to remove it and it's getting tighter, or breaks, because it's a left-hand thread, but most are right-handed. Hopefully this makes some sense. Pay attention when you're opening jars, which way. And try the right-hand rule, you discover that the lid really will move the direction of your thumb. Okay. Yes, so I'm getting instructions for the aliens. The hand with the thumb nearest to the side of your body with your heart on it is your left side. How do you know that their heart, if their heart is on a particular side, it's another artifact. And you can't be sure that the aliens aren't flipped relative to us. So you can't beat the artifact problem. It's the same with right shoe and left shoe. Try to tell the alien you've never met before, you've never seen each other, tell them which was their left shoe. Can't do it. All right? So I can now do the 5 physical quantities of rotation. Angular position is how you are oriented relative to a reference point. So we all agree on the reference. This can be 0, for example. And then you rotate by 90 degrees. This is 90 degrees up. This is 90 degrees toward you. Okay? Stuff like that. Angular position, not terribly important in physics. I mean, you care which way things are facing as a person, but physics is mostly boring. What's more interesting is changes in angular position, like this. My angular position is changing with time. I have an angular velocity, and that angular velocity is about 90 degrees per second. And that's part of it. This is 90 degrees per second, but again, we've got this problem. This is 90 degrees per second also. So we have to have the direction part. Again, angular velocity is yet another vector quantity with a weird direction. And the direction is, in this case, down. This is 90 degrees per second down. Okay? One of the problems for chapter 2 talks about another measure of angle, which you should know exists even if you never use it. It's called the radian. You ever encountered radians before? It is the fundamental, it's the fundamental unit of angle, and it's the one that everybody in the universe who deals with angles will know it enough. We'll know what a radian is. We'll all agree on the same value, what a radian is. Degrees are some crazy random choice. Why is a full circle 360 degrees? Where did that come from? Okay, so it's like, why not 370 degrees? Okay, radians fundamental. The full circle in radians is 2 pi, the famous pi, not cherry, but the pi of circles. And so this is actually a pi over 2 rotation. I've said it, we don't need to deal with radians. They're quite interesting for physicists and stuff, but we'll set them aside. You're more familiar with angles, so I'll stick with them. Okay, so this is 90 degrees per second up, angular velocity. We're okay with that? And what if I am not turning and I want to develop some angular velocity? For example, I want to develop some up. I need to undergo angular acceleration. So I have to pick up rotational velocity, and then now I have to give it away, slow it down. So angular acceleration is changes in angular velocity. And what causes angular accelerations? Well, it turns out there is an influence that causes it. Just as forces cause accelerations, there's something that causes angular accelerations. And the something is torque. And it's spelled T-O-R-Q-U-E, not T-O-R-K, which sort of comes to mind as the name of an odd, a rock singer, the Monkees, but that's before your time. All right. So T-O-R-Q-U-E, and if you ever encountered a torque wrench or something, that's the torque. So to cause angular acceleration, you need a torque. It's okay, what is it? It's a fancy name for a twist or a spin. When you twist something, when you open a jar lid, ultimately you're exerting a torque on the jar lid. All right? And just as objects have a resistance to acceleration, or a measure of their translational inertia known as mass, objects in the world of rotation, objects have a resistance to angular acceleration known as rotational mass. I'm going to call it, have been and will continue to call it rotational mass, because that gives you the idea. To physicists, it's got a fancy, awkward name. You may have bumped into this before. It's called moment of inertia. And there are reasons why it's called that, and it is more complicated when you get down to the calculating with it than rotational mass, but rotational mass is good enough. Something, this guy has a very small rotational mass, meaning I can make it undergo big changes in rotational velocity, angular velocity, very easily. Doesn't fight me. However, this guy, much more rotational mass. Okay? All right. So, just to give you some idea, I really am trying to do seesaws, although I've been talking completely abstract. In a seesaw, when the two of you get on the ends of the seesaw, one there, first off, you try to get it so that it can not undergo rotation and stay not undergoing rotation, like this. This I would identify as a balanced seesaw, right? And what is going on there, that means that when I got it balanced, the seesaw was experiencing no overall influence that causes angular acceleration. It was able to have an angular velocity of 0, for example, and keep it. And that's, most of the time on a seesaw, you're pretty close to that situation where the seesaw is set up so that it's got almost no angular acceleration. And how does that happen? Well, it's got almost no overall torque on it, no net torque on it. And so therefore it's moving as some sort of inertia had in mind. Well, now it's a rotational inertia. And so I can now sort of flesh this out with the first of the Newton's laws. Okay, there was the Newton's law of translational motion. That basically, you leave an object alone and it keeps the same velocity. If it was motionless, it stays that way. If it was moving, it coasts at a constant velocity. Remember, that's Newton's first law for translational motion. In rotation, it's the same story, almost. It's a little more complicated, but basically the idea is you've got a beam. This is a swivelly beam here. It's got a support in it to prevent it from doing any translational motion. If that pin weren't there, because this has weight, it would fall. So the translational motion would immediately show up and we would have trouble paying much attention, seeing anything interesting. So we support it in an interesting way so that it doesn't fall. And now it can only do rotational motion for us. And lo and behold, it's not rotating and it's not changing. So its angular velocity, and I accidentally and somewhat interchangeably say either angular velocity or rotational velocity, I don't care. The formal term is angular velocity. So the purists, of which not surprisingly there are physicists who are purists and will beat on you for using the wrong word. I don't care. See, record me, ha ha. Yeah, okay. I'm now on record. I'll be fired next week. So it's got angular velocity 0 right now, and it's staying that way. So the net torque on it must be 0. So this is an object that is free of external torques, the influences that affect rotation, and it turns at constant angular velocity. Right now that angular velocity is 0, but it doesn't have to be. It's the same as with translation motion. When you're at net force 0, you can be motionless, but you don't have to be. It's just you keep doing what you're doing. So let me get this guy going. And now it's inertial, but it's rotationally inertial. It's an object at rotation, continuing at rotation at constant angular velocity, which happens to be toward you. And it's not quite perfect because it's really hard to get rid of all the friction and such. All right? So there's Newton's first law for rotation. Leave it alone, as in no torques or no net torque, and it turns at constant angular velocity. Just keeps on rotating. If you want to change the rotation, you got to exert a torque on it. And the change in rotation, change in angular velocity, which is to say the angular acceleration, is once again a ratio. It's the torque you exert, the net torque on the object divided by its rotational mass. It's the same idea as Newton's second law for translation, but it's just for rotation. So instead of a force, it's a torque. Instead of a mass, it's a rotational mass. And instead of an acceleration, it's an angular acceleration. So if I twist this guy, so I exert the only torque on it, and I'll exert a torque on it, which has a direction, away from you, poof, I did it. I made it undergo angular acceleration. And now it's inertial, but during that twist, it was not. It underwent angular acceleration. Hopefully pretty straightforward. The last of the laws, Newton's third law for rotation, is for every torque, there's an equal but opposite torque. If you twist somebody, you take your neighbor and your neighbor's hand, be kind and polite, and twist them, they will twist back equally hard in the opposite direction. Every time. Same kind of rule. Interestingly enough, and this will show up I'll likely ask this question somewhere on one of the exams. When you're arm wrestling, you're twisting the other person, and the two of you are twisting really hard, and maybe you're perfectly matched and nothing's happening. Or maybe you're rotating and winning. Or maybe they're rotating and winning. Doesn't matter. Your torque on them is equal to, but opposite to their torque on you. So if I ask you what's the torque your hand, compare the torque your hand exerts on your buddy, your former buddy, versus the torque that person exerts on you, they're equal. It doesn't matter whether you're winning or losing or nothing. There are other things that involve who wins, but those two torques have to be equal and opposite. They are, again, on different objects. One's on you, one's on your buddy. Okay? So this is almost enough to do the seesaw in its entirety. a couple things to look at first. To get translational motion and rotational motion separate, you sometimes have to be a little careful. An object can simultaneously undergo translational motion and rotational motion. An example, this. I'm going to spin it and throw it, okay? So now it's doing that, the arc it traveled in, right? Let me throw it in an arc, okay? That was the arc of a falling ball. It was traveling in a nice, it happens to be a parabola. It was doing the usual things. It was coasting horizontally and falling vertically. At the same time, however, it was spinning steadily about some point. So it had a steady angular velocity because nothing was exerting a torque on it. All right? So it was doing both at once. Wow, it's clever. It can do that. To let you see how complicated that arrangement can be, I mean, that ball is spinning. Well, let me do it this way. The issue is finally, when it's traveling in an arc, what part of it is traveling in an arc? Because if you look at the motion, say, of Wilson here, Wilson! Okay, if you see Wilson here going in the arc, Wilson's whipping all over the place, real complicated motion. Similarly, the spinning, what point are we talking about? There is a point in the ball about which all the mass is balanced, and consequently, that mass travels very simply. That point travels in a simple, the arc of the falling ball. It's known as the center of mass of the ball. So the ball has this location. Any object has a point in space known as its center of mass, about which all the mass is sort of evenly distributed in some respect. And when you throw it, it rotates about that point as that point travels in the arc of a falling object. So from the perspective of translational motion, it's as though the whole object is right at that point. From the perspective of rotational motion, it's as though the object, that point is special. That point sort of stays put during the rotation, and everything else revolves around it. So in a ball that's properly made, a conventional ball, that point is dead center. And it is the center of mass. It's a term you've probably heard before. That's where it is. It's the natural pivot of an object, put it that way. So this guy's got a natural pivot at its center, so does the bowling ball. Not so for this goofball. The goofball has most of its mass here at the end. Is it sand or water? So this guy, if you spin it, it spins around its center of mass, which is on its surface. Woo! Right? It's hard to catch because it behaves unpredictably. Well, predictable, but hard to identify way. So it flips around its center of mass. So far, okay? Why? Questions has come in here, several questions actually. Fifth physical quantity of rotational motion. Let me make sure you're all on board with that. Angular position, angular velocity, angular acceleration. So angular velocity is the rate at which angular position is changing with time. Angular acceleration is the rate at which angular velocity is changing with time. That's three. The influence that causes angular acceleration is the torque, and the resistance to angular acceleration is rotational mass. Five quantities. Next question that's in here is what's the difference between center of mass and center of gravity? And they are used in common language interchangeably, but they're quite different concepts. Center of mass is the natural pivot of an object. Go into deep space where there's no gravity, spin a basketball, it'll spin around its center. Spin this goofball, literally called the goofball, okay, so I can't just make jokes about it. It will spin around that surface. It'll look wacky in deep space. So center of mass is strictly an inertial quantity. It has nothing to do with gravity. Center of gravity, however, is the effective location of an object's weight. So my center of gravity, my hand has weight, other hand, my head, my knees, if you look, basically average over it, where's my center of gravity? It's somewhere in here. I can't touch it. It's inside me. But that's the effective location of my weight. And it's entirely a gravity concept. No gravity, center of gravity means nothing. All right? They happen to lie at the same location for any object here near the surface of the Earth, any normal-sized object near the surface of the Earth. Why? Because every kilogram of mass develops 9.8 newtons of weight. So my hand has mass, it also has weight. My hand has mass, it also has weight. Head, likewise. And if you look for where's my mass distributed, it's right in here somewhere. You look for where my weight is distributed, it's right in here somewhere. It's the same location. So they happen to they coincide, but they're different concepts. Is that okay? And therefore they're used interchangeably, which sometimes drives physicists and sometimes me a little nutty. It's like, oh no, and you hear on television, no, they call it the center of gravity, or they call it the center of mass. Nope, that's not it. All right? So if it's an inertial thing, it's center of mass. If it's a weight thing, it's center of gravity. Okay? Why does a tennis ball with a lot of spin seem to have center of mass? The center of mass doesn't travel in a simple arc. Because of air. We will eventually get to what happens when a falling ball is moving through the air. It pushes on the air. If it's spinning, it pushes on the air, and it curves. And tennis balls are famous for curving. I mean, they put topspin on them, they dive into they curve down. Golf balls, you put backspin on them, they curve up. Baseball pitches, you curve them, they curve to sides. And we'll do that, but that's in our future. All right, other questions? So, in the absence of air, objects very clearly spin around their center of mass, and that's their natural pivot. What I want to show you is this, which is the lecture demo guys, Al, who often is saying so, created. So this is an object with its center of mass here, and another light just to show you it rotate. If I turn these lights on, 1, 2, and I toss it, what will happen is its center of mass, which is this location of this light, will travel in the arc of a falling ball, because as the rest of it pivots around that center of mass. So the center of mass is simple. Its motion is that of the falling ball. Let's try it. Can you see it okay, or should I dim the lights? I'll dim the lights, because I can, right? All right. So presumably the red light traveled in a nice arc, while the blue light went blobbing around it. All right? So objects naturally spin around their center of mass. And if you tack the center of mass in place, so translation just disappears from the story. And that's what a seesaw does. A seesaw supports you and the riders right at the center of mass so that you can't fall. That's actually center of mass, center of gravity. There are different ways to think about this. And I got to be careful I pick one that works. Here, the center of mass of this board is definitely right there at the center, and we stuck a pin through it. So it can't undergo the arc of a falling object. Basically, it can't translate. Its center of mass can't translate at all. All it can do is spin around its own natural pivot, which is stuck in place. All right? All right, so where this is going with the seesaw. The seesaw is an object, again, supported at the right place so it can't translate. And the kids sit on it in such a way that it's experiencing no torque due to gravity. And now I got to tell you why there would be torque due to gravity. Because gravity exerts forces on things. And this is the world of rotation. Where'd the torque come from? All I've got is weights, which are forces. Well, I told you before that you can look at rotational motion in terms of all the translation motion of all the little parts. You can do it. It's a mess, but you can do it. Similarly, you can describe translational motion in terms of rotation of all the parts, but it's a horrible mess. It's a kind of, yeah, you can do it. Similarly, it turns out that you can describe, or you can look at a torque in terms of forces, and forces in terms of torques. They're not the same, but one can cause the other. You can use forces to create a torque, and you can use torques to create forces, and we do it all the time. For example, and this is one from the book, my classic one, how do you open a door? So just imagine a door that can swing both directions. They do exist. You got a doorknob on it. You can push it and pull it, but you can swing it around the hinges. It undergoes rotational motion about those hinges. And you make it undergo that rotational motion through the use of a force on the doorknob. You take the doorknob and you push it. And as you push it, your push somehow becomes a torque that causes the door to undergo angular acceleration. Or not. If you push the wrong way, the door does not undergo angular acceleration. For example, if you take the doorknob and push it right towards the hinges, doesn't work, right? This is an ineffective way of getting the thing to start rotating. Similarly, away from the hinges. Instead, you want to push on the doorknob kind of at right angles to a line between the hinges and where you push. So if you look at the face of the door describes lines. And you come out here at a distance from the hinges and you push on the door, and you push at right angles to that door face, you can get some angular acceleration. More observation about door. If you don't come out to the doorknob and push at right angles to that line, but rather go over to the hinge and push, nothing much happens. And you've all done this too. You come to a door and you can't tell which side is the hinges. So you push on the wrong side and nothing happens. So the long and short of it is to produce a torque using a force, you need leverage, you need a lever. And what you do is you come out, and so now let me do it here. Here's the pivot. This is like the hinges on the door. And I'm going to come out to the doorknob, could be out here. And you want to come a distance away from the pivot, and you want to exert the force, but not in any old direction. You want to exert the force at right angles, or something close to right angles, from the relative to the line, from the hinge to where you push. So from the hinge to where you push is not only a line, it's actually got a direction to it. It's a vector. It's got a name. It's called the lever arm. So you want to come out here to the lever arm, and you want to push at right angles to the lever arm. And when you do that, the torque you produce is your force times the lever arm, considering that the only right angle parts count. So the farther you come out here and push, actually the more torque you produce. That's the concept of a lever. If I push in here, close to the pivot, I can push pretty hard and I barely get any angular acceleration. But if I come out to a longer lever arm and push, much bigger torque as a result. So this shows up really in lots of lever situations. If you want to produce lots of torque and all you've got is a certain amount of force to work with, get a long lever arm, because the torque you produce with the force is proportional to the length of that lever arm. It happens in seesaws. I'll finish up by balancing the seesaw with a big kid, little kid. And it happens in seesaws, but it happens in so many things of everyday life that I'll talk about, I guess, down the road. If you got a heavy kid, if you put the heavy kid, sometimes I remember to bring a big weight out here. The heavy kid and the light kid at opposite ends, what they're doing is they're producing torques on the seesaw board that cancel. They're trying to. If they cancel, the thing is experiencing no net torque. It's inertial. In this case, that's not true. This kid's too heavy. The torque this kid's producing is too big. So what do? Shorten the kid's lever arm. Put them toward the center. And now you can balance it again. They're both exerting torques on the board. I will talk next time about the directions of those torques. They happen to be opposite. and it's balanced again. This kid is producing a torque that way toward you using a small weight, that is small force, and a big lever arm. This kid is producing a torque away from you using a big weight, big force, and a short lever arm. The product of the two, force times lever arm, is the same. The directions are opposite. Okay, so I'll stop. Have a nice weekend, and see you on Monday.